Hi, good evening, everyone. So, those who have attended yesterday's class, so we were we have completed the week four theory portion, and today we will continue with our coding of we were trying to solve the image classification with transfer learning problem, and after completing that, we will continue with the image segmentation with unit. Okay, in today's session. So. I think so. We were stuck on some code snippet yesterday. So I have fixed that today and we'll continue it from there itself. Okay. Yeah. Everyone can see my screen, right? Yeah. Okay. So we had, I'll just reconnect it once. So we are working on the image classification with transfer learning. So just to give the context, we have a data set with us that has three classes, Visa, Sushi, and Steak. Okay, so we are trying to do that only. So this is the libraries that we are going to use. So just execute. This is being run. Till then, what is the data sets? So we defined a proper. So yesterday we have covered these things, but I'll just cover it in 5 to 10 minutes. So this is the download dataset how a function which will work at any place. So we are extracting this from a particular GitHub zip file and we are extracting it. Once the zip file has come to us, then we don't need that zip file. So we remove the target source. Okay. So we delete that, remove the source. After that, we have our dataset with us. Now we have that. Then we saw that how we can explore the dataset. We tried to calculate some simple statistics like class statistics, what is the split statistics, and what are the total number of samples. Okay. So we have also covered this code base also. So this is the train set with us. So there are these many samples for steak, pizza, and sushi. And total there were 225 samples for train set and for test set. It was 75 samples. If you can also go in here data, pizza, steak, sushi. Inside that, you have test and train. The split has already been done for you. So for each of them, inside this, there is an image. Again, same for the test data set also. These are the images. Okay. So this was done. I think so. We had completed this much last time itself. Yesterday we got stuck at this place. I think so. Yeah. So what the problem was I had not defined the class names. ImageNet mean and standard deviation was present below. But these two things, class name and test transform, these two things were not available to us yesterday. So after fixing those part of code, now this is running. I have checked that. So I'll just go through this and we'll go from here. We'll just go one by one and we'll cover the entire code that professor has written and he has explained few parts. We will explain them in complete details what each of that line is doing. Okay. So what we are doing here is we are trying to visualize the samples from the given folder and we are taking this data path. So basically we are trying is for each of them at least we should be able to see some what are the sample images that are available to us. So the plot figure is figure 10 cross 10. We take a canvas of 10 cross 10. We see what are the image paths. So what we are doing is for each of the class name, go to its train part. Inside the train path, because generally it is said that for the test set, you should not see whether we should not go into the data set in the test part and see what are the images if it is for the image data set or if it's another it can be of many things like it can be features if you are doing an ML algorithm. So it is better not to review that before getting your model. Okay. So class path has been defined for train and for each of the class name. You just have to extend it. Either it can be a .jpg or it can be a PNG. Then we take random image paths. So these paths can be any of them. We are just taking three right now. So for I and image path, enumerate random image paths. So from here you will get only three paths. Okay. So then you open that image and convert it into an RGB scheme so that you have three channels. So it will be, if the earlier your image is just 2 cross 227 cross 227 height and width, then now your there should be 227 cross 227 cross 3. That is the three channels for RGB image. After that, you transform the image, and whatever is the transformed image, you have to change it to the standard view using the torch and sensor. And we have to permute unnormalized image. What happens is when you do this part, right? Image conversion and transformation, then what you get is C cross H cross W. What is C cross H cross W? It is in the form of channels, height, and width. Then what I'm doing is I'm just converting it into height, width, and channels. Okay. Then from 1 to I plus 1, I'll just show that image, and also I'll put an image title to it. And axis has been defined as false. And finally, I will show this using the matplotlib library. Okay. So yeah, so you can see I'm getting that sushi steak. Yeah. So this I'm getting now. So this part is working for me. Next, till this part we had covered yesterday. We'll continue from here now. So create the transformation pipelines. So now every image, we know that every image is available to us, but to make sure that it goes into the pre-trained model properly and we get our desired results, we have to make some conversions. We have to transform few things. It will see what are those things. And so it is better to make a generic pipeline which will take any image and that will convert it to the desired output, so that that desired output is eligible enough to go into the model. Okay. So image net mean and standard deviation we are using. These are the fixed numbers, so we don't have to do anything about that. So these are the RGB channel means and RGB channel standard deviation. So it is about how much importance you are giving to each of the channels. Okay. So train transformers. So it is a transformer dot compose. That means we are keeping one set pipeline for that. So first of all, you resize this to 224 cross 224. So I think so the model that we are going to use for this is efficient net, and efficient net requires the standard input size of 224 cross 224. Depending on the image, whatever model you are going to use, you have to transform the image to that particular needed pixels. Okay. So now what we are doing is, now from here, this code line, random horizontal flip. Now, what says that it says that with 50% probability, just flip those images horizontally. So 90-degree it will go. Okay. Then do some random rotation for some of the examples. Degrees plus minus 10 degrees. Transforms color dot jitter. So this is augmentation. What happens with augmentation? So you can see whenever you click a photo in your phone, you can increase or decrease its brightness. You can change the contrast, saturation, hue. These things are available in our phone as well. Whenever you are trying to edit a photo to post it somewhere on the social media or something like that. So that process is known as color augmentation. So we generally, so why we are doing these things, these four things that we did here, specifically these three things. So it might be possible that every time you don't get an image that is perfect. Okay. There might be some images which are blurred. There can be some images which are just simple flips, which might be 180-degree flip. So it should not be in such case the model should not work. It should not be like that. So for to make it robust for any kind of changes that are possible, we try to keep these things in mind that inside the training set itself, we will make some changes and we'll still make sure, because for training set I know the labels, right? So since I know the labels, I can learn it. The model can learn it. Okay. So this helps to do that. And finally, I'll convert the entire whatever thing I did to a tensor. Okay. And we since now once we have the tensor ready with us, we have to normalize it with the mean of image net mean and standard deviation of image net. Okay. Now, these things are not required. Just remember, these three things are just required for the trained data set. We don't have to change anything in the test data set. These things are not meant for that. So in the test data set, we just resize it because resize is important because otherwise it will not go inside the model itself. But to go into the model, we need to resize it. And finally, we change it to a tensor and normalize it with ImageNet mean and ImageNet standard deviation. And finally, we create the pipeline. So now what we will do, we will see here what is the training transform of how many operations are there, testing transformer operations, and what are those transformations. Okay, so I'll just run this cursor. So training for transformation has 6 operations and testing has 3 operations. You can see from here also 1, 2, 3, 3, 4, 5. This is the 5. This is 6. And these three will not be present in test. Therefore, it is 3 operations. You see, resize, random horizontal flip, random rotation, degrees -10 to +10, color jitter, we change some of the things here and we convert it to tensor and normalize it. For the testing pipeline, we are just going to resize, convert it into the tensor and normalize it to the ImageNet mean and standard deviation. Okay. And next, under this itself, what we are doing here, we are data visualization and data loading. Okay. So now we will load the data set. Okay. So, okay. So now, if you remember in the previous week also, you had this data loader concept, right? So the tensor does not, so like when we you generally do in sklearn library, so if there is a sklearn, you say just xtrain, ytrain, those kind of things are there. But what happens differently in PyTorch is PyTorch does not means it works as that also, but it is tedious. So it has its own data loader and it is preferable to, so you can see here that data loader combines a data set and a sampler. Now what is sampler? So that it does not remember the flow, how each of the images are coming. It should be a random sampling. Okay, an iterate provides an iterable over the given data set. The torch.utils.data loader supports both map style and iterable style datasets with single or multi-process loading. So this is how the data loader works. Okay, and I'm importing the datasets as well. We already have the dataset, so that we will be using this only. Otherwise, there are some pre-built datasets as well. I think so. In the next example, that is of the image segmentation that we will see, that has this. I think so. We have to use the dataset from there on. So def create and datasets and data loader. We have created a specific function for that. Data dir. It will be the path from where the data is coming. Then train transformers, transformers.compose. We have already composed these things, right? See, transformers.compose, train transformers, and transforms.compose, tensor. Then batch size. What is the batch size that you would like to have? Number of workers. So this is basically the course of GPU that you want to make it parallelize, those kind of things. Currently, don't focus on those things. We have to just focus to have a trainable element first of all. And shuffle train boolean is equal to true. Shuffle train, you would have seen. So basically, we want that the model should not bias to a particular sequence of images coming. It should be independent of that. It should be able to perform very well, even though if or not it has the like knowledge of the sequence of images coming. Okay, so this is shuffle train. Next is train dataset. How you define the train dataset? We call the datasets torch datasets dot image folder. I already have this, so this is my root data dir. Inside that, I have this train and transform. I'm going to use is the train transform. And similarly, for the test dataset, I'm going to use test transform. What are the class names? Class names comes from the train dataset classes itself. In our case, we have 3 classes. Those are pizza, stick, and sushi. So train load data loader. So it will run the data loader on the entire thing. The data set is a train data set. Batch size that we have defined is 32. Shuffle train, that is true. Number of workers remains 0. And memory is true if device is CUDA, otherwise false. So it will work on CPU in our case. In test loading, another important thing that you have to remember, the shuffle will be false because no shuffling is required for getting the consistent evaluation. So number of workers is equal to number of workers. Pin memory is equal to true if device is equal to CUDA, otherwise we will say it is false. And we are just going to now get a summary. What were the number of training samples, testing samples, number of classes, class names, batch size, training batches per epoch, testing batches. Okay, just run this. So training samples, as we have seen earlier, 225. Testing samples is 75. Number of classes is 3. Pizza, steak, and sushi. Batch size is 32. So if you see 32 into 8 is, I think so, 6, 256, right? So there will be 8 batches per epoch, and the testing batches will be 3. So 30, you have to take the, I think so, you have to take the seal of that. When you divide number of samples divided by batch size, you have to take the seal of that. That will be your training batches per epoch and the testing batches. So yeah, this is the pre-processing step required for the, now with this, we have completed the pre-processing step. If you have any doubts so far, please let me know.
Sir, from this, what kind of questions we can expect in quiz?
Quiz, you should. That's why what we are trying to achieve is that from week 3, week 4, that you should know what each of the code line is performing. When shuffle is needed, when shuffle is not needed, what is the difference between evaluation mode, testing mode, and training mode. So those differences you should know clearly, and you should know the each of line what it is performing, what it is trying to do. And in NPP, you have to write these things. You have to write the entire customized neural network model. Okay.
So when is NPV? Is it in December, right? December.
No, 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 no. After quiz one, there will be one NPP. After quiz two, there will be one NPP. Yeah. Chandrasekhar, you were saying something? No? Okay. We'll move ahead. Next is pre-trained model. I'll just hide these things. Data visualization is done. Next is the pre-trained model. Okay. Syllabus is week 1 to 4, right? So for the weights, so if you remember, yesterday in the theory portion, we had discussed what the concept of transfer learning. So transfer learning can be of two types. One is the, in one we freeze all the weights and we just change the classification head. And in one we have to unfreeze all the weights and we do a full fine tuning. Either we can do a partial fine tuning or we can do a full fine tuning and get our desired results. Okay. So we'll be using the weights of efficient net B0 model, and we take the default weights of that. That is the best available. So where does this efficient net is present? It is present in the torch vision.net. So this is the reason why we have imported torch visions. We can get models and data sets from here. Okay. So like just like sklearn has, I think so for sklearn there is a data set is inside that only, and models also you can call from like linear regression, from linear regression till XGBoost you can call most of. I think so for XGBoost you have to import it from outside, but most of the like main models are present inside the sklearn library. Similarly, there are available in the PyTorch library as well. So now what I do is I'll just save that entire model to our device, and you can go through this. So it is not a very big thing. Just go about. So this is the entire model, model of the efficient net. So it says that at the 0th level you have a con 2D norm activation. Inside that you have a con 2D, like three channels are there, 32, kernel size is 3 cross 3, stride is 2 cross 2, padding 1 cross 1, and bias is false. After that, you perform the batch normalization, and instead of we have seen yesterday in our theory portion that AlexNet uses the brought the concept of ReLU, right? ReLU activation. Now here it is SILU. Okay, so similarly, then we have, let's say we have a sequential. Now after con 2D, we have a sequential. Then again sequential MB con 2D sequence excitation con 2D. Again, similarly, it goes like this, and it has the entire how many things what will happen at each layer. So it is not important for us to know, but you should read this because for now you have to understand how each of the convolutions are happening. Okay, so I'll skip this part. Yeah. After that, you can also import the summary for the all the for this model. How many if the model input size is 3 into 224 cross 224, which was their desired input. So we can run this. Okay, I not run this. Yeah, yeah, I downloaded and now it is present. So I'll just hide the output for this. Next is we see the torch summary. Okay, now you see where it is. Yeah. Okay. I'll just take this. Yeah. See, in the first layer, we have the conv 2D layer, the output shape. So input goes is 3 into 224 into 224. And the output from here is 32 into 112 into 112. And how what is the number of parameters? Similarly, it goes like this till the end. If you see, so finally you have there are total 255 layers, and that is the linear layer where you will just classify into 1000 categories. You remember yesterday we talked about this ILC VRC competition from where all these state of the art CNN architectures were introduced, right? So finally we have the linear layer 255 that classifies that softmax probability, gives a softmax probability for the given image in the 1000 image classification. And most of the time the maximum parameters are in the fully connected layers only. If you see above, there are very less. Okay, so as and when you go down below the um, like complexity architecture, then the number of parameters tend to increase. If you just see, entire model is just approximately 4 million parameters, and only the FC, that is a linear layer, has approximately 1.2 million parameters. So then the total number of parameters is 5 million, 5.2 million, something around that. So your input size is 0.57 MB that it requires. It should be less than or something equal to that. And forward pass size is 173 MB. So this is why it is important, because if you have a GPU, then you have to make sure that the resource optimization is there. You have to make sure that within your available GB of GPU, you should be able to train the entire forward pass, and the mm, parameters should get updated. So that is the back propagation. The estimated total size is 200 MBs for this particular model. We don't need this, so I'll just hide this. Yeah, Chandra, please tell.
Sir, param size was 20 MB, but total size was 170 MB. So what is the difference?
No, no, I think so. It is more just a minute.
It says param size 20 MB, but total size is 194 MB.
Yeah, because we have to do the forward pass. Now, param size is only the back propagation. When you come back and update all the weights,
Okay, okay.
that are the number of parameters that you have to update. So these are your trainable parameters, most of them.
Okay, then sir, what is 173 then?
173 is the forward pass. For each of the convolutions, see, there are 255 things that are happening, right? There are 255 layers in this. So in each of the layer, that itself will have some particular weight, right?
Yeah.
So that is the weight for that only. So if you see the 173 divided by 255, each of the layer is will occupy some of the spaces, right? So it has a particular number of operations going on inside that. So it will do some
Uh,
kernel, it will take a kernel, it will slide over that image and it will get some output. So those things occupy some space, which is mostly less than 1 MB for each of the layer.
Sir, trainable parameters is 5.2 million.
Hmm.
So effectively in forward pass, we are basically changing those parameters, right? And backward pass also, we would be changing all the parameters, right? So why it is only
No,
less?
no, in the forward pass, we don't change anything, right? We just go on calculating everything. In the back propagation only, we change the parameters of the waves or the wave.
Mhm.
We don't change. So they both are different. In why you are going, you just take a particular input image and you go through a series of convolution max pool layers, and finally you get to a place where you get a particular you get the classification of the image whether it is dog or cat. But when it after it tells you that, let's say this is it was a pizza and it was correctly classified as pizza, that means your model is fine, right? So it will now start going back and okay, whatever weights it calculated, it will just make sure that it gets replaced. Earlier, let's say I initialized with some random values. Now it will get replaced with the value that I calculated it this time.
So, what you mean is that in the forward pass, all the calculations which we are doing,
Hmm.
that requires space, which is we see here.
Yes,
And in the backward propagation, we are just adjusting the weights because of the
yes,
derivatives.
yes,
So that is related to this 20 MB.
yes, yes, yes.
Okay, sir.
Okay. Yeah. Okay. Okay. So next thing is I'll just hide this output. Yeah. Now what we are doing is for param model features dot parameters, I have set the entire thing param dot requires grad is equal to false. This means you don't have to update anything in the back propagation. The all the weights have been freezed. All the weights of the this model efficient net, whatever I took the default weights, the best possible weights for this model have been fixed now. Okay. So yes. Uh, it is. Yeah. And so if you remember in our thing that we talked yesterday, we are using that. The first example of the transfer learning was that you have to freeze all the weights and you just have to classify into the um, classify on the basis of what you have to just change the classification head layer. Only the last layer will get changed and nothing else. Okay. So torch. Okay, I have to run this also. Yeah. Next is we have to set the manual seed. If you are using a CUDA, then for CUDA we use torch.cuda.manual seed. If you are using a CPU, then torch.manual underscore seed will get fixed. So output shape is length of the class names that you, if you remember, it is three only. And model classifier. Now I'm just changing the if you, this is the particular line where we are changing the classification head. We change the model dot classifier and I say that it will be a sequential thing. First you do a dropout and finally there will be a linear layer. We are just changing this linear layer. You remember? Uh, yes, I think so. It was present in this. Yeah. Yeah. We are changing this. So this was minus 1 comma 1000. Now if you check later, it will become minus 1 comma 3, right? So hide output. Yeah, input features in 1280 because at the 254th layer, my output was 1280. From 1280, now I have to come down to 3. Output features is output shape, that is the same number of output units as our number of classes. Okay, and bias is true, dot to device. So I'll just run this. Yeah, this is done. Now when I write this summary, we have to just go, everything will remain same. Now as you minus 1280 came, my linear layer will take the input of 1280 and my output will be 3. Now you see there is a huge difference between this number of parameters that gets updated. So approximately 1.2 million has gone now, and we have just left with 4 million parameters. And also another important thing to note is the trainable parameters is only the last layer 3843 that is present in the linear layer. The entire other parameters that are left, so total parameters minus the trainable parameters are non-trainable. Why? Because we have decided to freeze them. Okay, I hope this is clear. And now I'll also call the transforms from the weights or itself. So whatever we had decided to do. So we are doing a crop size to 224, resize shape to 256. We are using this mean and standard deviation of the image net related to efficient net, and we do some interpolation mode by Q. Okay. So this is the entire portion for pre-trained mode. Yeah. So any doubts in this portion, please let me know. Yes, guys, any doubts? Otherwise, we'll move forward. Okay. Yeah, so pre-trained model is done. After that, we have to do the training the model. So I will bring from what sir has said. Yeah. So first step, we define the loss function and the optimizer function. So we are using our loss function as cross entropy loss, and our optimizer is Adam optimizer. We'll use the parameters that represent in the model because this is the place that has to update the parameters, right? There are 3,843 parameters that have to be updated. Yeah, Subra, please tell. Subrat,
Hello, am I
yeah,
audible?
please. Yeah,
Yes, yes, sir. Sorry, sir. I just wanted to ask, like, what other type of loss function, like, can we use for this particular model?
so it does not depend on the model, which particular loss function you want to use. It depends on the main goal. If you want to achieve a regression task, you generally use mean squared error, mean absolute error. These are the common things. There are
Yes.
multiple types also. And if you are doing a classification, cross entropy loss, then you can have loss functions are, I think so. F1 loss is also there. So it depends on that. Based on that, you have to do something.
Okay, sir.
Yeah. Any other doubt?
No, sir.
Okay. Anybody else? Okay. Uh, yeah. So loss function is nn dot cross entropy loss. Optimizer is torch dot optim Adam, and we take the parameters that have to be updated, and we are saying that the learning rate will be 0.001. Okay. So next is the train step. Okay. So this will be a bit long code. Just let me see. Yeah. Hmm. We'll go through this one by one. Okay. So this is the train step that we are going to define. We are using a model that efficient net that we brought, data loader. we have defined the data loader for both train dataset and test dataset. Loss function for us is the cross entropy loss. So we have not called it yet. Optimizer is the tossed Adam optimizer. Device is CPU that we are using. Okay. Model train. So we start in the set the model first for the training mode. Okay. And we'll check the train loss and train accuracies. We'll start with 0, comma 0. Okay. Now you have to loop through the data loader for every batch. Okay. So for batch x comma y in the data loader, you have to just change, first of all, set the x to CPU and y to CPU. You make the first forward pass. Now your model, this x goes into the model and you calculate some y prediction. Okay. Now with based on that y pred and the original y that you had, you will calculate some loss. You will have some particular loss value when you put that into the loss function. If you remember, this is the cross entropy loss that we have. Finally, you just add that particular loss item to your train loss. Okay. After that, make the gradient 0. Whatever the gradients were accumulated till now, you just make those gradients 0. And then you compute the loss backward. Once you compute the loss backward, you have to update that with the help of your optimizer. With this, you will be able to update your parameters while going backwards. That is the back propagation. Finally, you will accumulate and calculate all the accuracy metrics from all the batches. So what you are doing, you are taking the argmax and what is the most suitable Y prediction class for this particular image. And you have to update the training accuracy after you get that. Okay. So yeah, this is done. Now you have to adjust the metrics to get the, we are not adjusting per se, we are just calculating to get your average loss and average accuracy per batch. So this is the training loss divided by the length of the data loader. That is, I think, so 32, and this is also 32. So it gets divided, and you get the average values. Okay, now this is your test step. We'll just remove this. So now your model is in the evaluation mode. That is your test mode. So inside the PyTorch, we don't call it test mode. It is known as the evaluation. Similarly, you will just set up the test loss and test accuracy values, that is 0, comma 0. Now you have to turn on the inference context manager. What we are doing is from inference mode, inside the eval mode, we use the inference mode. So what inference we are trying to do? We are trying to come up with a classification for your test image. Let's say we don't know that, then, but right now we already know that whether it is a pizza stick or sushi. With the help of that, we say that how well or not our model is performing. So we'll go through the data loader batches, that is from the this time from the test data set, and send it to the target device. You make the forward pass, you accumulate and calculate the loss, add the loss to the test loss, and finally you calculate and accumulate the accuracies. You see there is a difference. Here what you were doing, you were first zeroing out the gradients, whatever the were calculated till now, and then you do the back propagation and update your parameters. In test, we don't do that. We just directly from test loss, we go to the test predict tables and finally calculate the test accuracy. And similarly, like we did for the training step, similarly for the test step, you have to calculate what is the test loss and test accuracy, what is the average metric for that. This is our entire train. Yeah, Chandra, please tell.
Sir, if there is class imbalance, right? So is
Yeah.
accuracy the correct way to go about here?
No, then you have to use some smooth sampling kind of thing. But currently, we don't have that. We had seen in yesterday's session itself when we did that um, train is to test ratio. For that only, this particular thing called train is to test ratio was calculated. And since was train of the test ratio was more or less good, I think so it was 2 is to 1, 3 is to 1, something like that. If it is uniform, then that means that you don't have any sampling problem. Or that's like any particular class being more in number and any other particular class being less in number. So that's for that case, we don't have to worry. Otherwise, if as you have pointed out correctly, if there is a class imbalance, you have to make sure using smooth or some different kind of procedure so that your sampling is perfect.
Okay.
Okay. Next is train. So here we'll just create a dictionary, and whatever definitions that we have said above, na, that will just get run here. Okay. This is kind of the moment of truth where that everything you have written so far, now you have to just run that. Okay. To print out what's happening, update the dictionary, and finally return the results to us. Okay, I'll just go through this once. So results, we are train loss, train accuracy, test loss, and test accuracy. We have saved the model to the device. Now TQDM, if you remember yesterday, I told you what is the importance of TQDM. So whenever you train a model in build, it does not have any procedure to showcase how much it has trained, right? So for that purpose, generally we use TQDM. It will tell you, it will give you a progress bar. So if you have seen in Windows, old Windows, there was 0%, that progress bar is there, no 1%, 2%, it goes on like that. Similarly, you use the TQDM in PyTorch library. Okay, train loss and train accuracy. You just go through the train step. Model, data loader is your train data loader. Loss function is a loss function. Optimizer is optimizer, Adam optimizer. Device is CPU. Test loss, we don't have a loss function. We have the loss function, but we don't have the optimizer for this. Okay. So we'll print for each of the epoch what is the train loss, what is the train accuracy, what is the test loss, test accuracy, and finally we'll append it. And when you are appending it, you will finally calculate the what is the average metric for this. Okay. So let's run this. Okay. Why didn't it show me anything? Okay. Okay. Yeah. That will be the next code. Yeah. It has trained everything. It has not trained. We are just defined the function for now. We have to train it now. Okay. So we have set the seeds. We are using a timer. We are using a timer to see how much time it takes and set up the training and save the results. And the timer we are training it till 5 epochs and total training time in seconds. How much time it takes? Okay. So let's see how it does. Okay. Yeah, Subrat, please tell.
Sir, it's a small doubt. I mean, I just want to know what is the meaning of that X dot two device. I mean, I'm not like what it. You said it like what does that do?
Can you tell me which part you are referring to?
Sir, in the testing code in the loop, yes, 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 the X comma Y equals to X dot two device comma Y dot
Yeah,
two.
okay, okay. So what happens is, if you remember in the first week, it was told to you that there is a common error that happens in PyTorch is that you might forget where your model was and where your data set. But in my case, currently everything is on CPU, which is a bad choice. I think so. It might crash also. We'll see what happens. So what we are saying is then you have to just make sure that your X and Y should be to the device on which you are performing everything, where your model is saved. Wherever your model is saved, you have to send everything over there. So just to make sure those people who use CPU and GPU interchangeably, it is important for them, not for us. For you, we whatever we are doing it at one place only. Okay, so we'll see what is
Sir,
happening.
and what? Oh, okay, and sir, just what is the meaning of inference mode and eval mode? Like that you explained
Yeah.
in that
So
form.
eval mode is known as the evaluation mode. That is the testing mode, in which what we are trying to we say the model is that now since you are in the testing mode, you don't see. You saw that there are differences. There are huge differences between the training mode and the test mode. So you can think of
Yes,
evaluation mode as the test mode itself. So in training mode, you are doing some back propagation, you are updating the weights, but in the test mode, you don't do that. You just calculate the loss and you just move on, right? We are not here to
yes,
change the model parameters in during the test task. And inference, along with that, it does the inference. What is inference for us? So instead, or just don't leave, in layman terms you can define this as, just don't leave the model that just by calculating the loss, you should be predicting. So my whole point of this task was to predict which class it belongs to, right? If you remember, we
Exactly.
had this pizza, steak, and sushi. So my end game is that I have to make sure that it should classify my items correctly, or at least forget about correctly. Obviously, the final goal for the model is to get best results, but at least tell me what you are doing. If it is a pizza, are you able to do it as a pizza, or you are changing it to something else? So that is known as the inferencing. Means based on your model, what are you trying to achieve? Like what is the inference that you are getting? So when you are using ChatGPT, right? When you are using ChatGPT, it is mostly in the inference mode only. It is based on your question. It is giving you some answers, right? It is a text completion kind of. So it is best at what it does. So that is what we are doing here. Is it clear, Subrat?
Yes, sir. Thank you.
Oh, okay. Okay. I think so. Our model has trained. It took around 161 seconds. That is approximately 3 minutes. If you would have done it on GPU, it would have done much better than that. Okay. Now you see across the time period how it has gone. So training accuracy has moved to in Epoch 5 it has gone to 0.76, but test accuracy is very high. It is 0.9072. Okay. So okay, good. Whatever was there, fine. Now we will see how our we have trained the model. It's now it seems, but we have to see with some visualization how it is working. Okay. So we have to evaluate this model, and we can do so by plotting the loss curves. So we'll do the same thing now. Um, Plot the loss curves. Okay. Okay. We don't need this. The class. Okay. I'll just explain what this is. So we are defining a function to plot the loss curves. So we'll say loss is results from test train loss. If you remember, these are the things that we got. We got four things: train loss, train accuracy, and test accuracy. So similarly, we create the variables for the same. We calculate what is the total number of epochs. I think so. There were 5 epochs, and I'll create a figure, and we'll show both. For testing, we'll show what is the loss and what is its accuracy, and for similarly for the train also. But what we are means here, what it is doing, it is loss with respect to epochs and accuracy with respect to epochs. Just run this, and finally I'll just call this function. That would be plot the loss curves, loss curves, and I have to put the results in this. Yeah. So we have a good looking chart. Okay. So this is for the losses. You see train loss, it started somewhere from 1.1 and it has gone to somewhere between 0.65 or something like that. Okay. And test loss, it started even better. It started below 1, that is 0.95, something like that. And it goes up to zero point 0.6. And this is done in 5 epochs, 0 to 4. So if you consider 1, then it becomes 5. If you consider 0, then it is a 4. And accuracy is a up curve. So you try to get better and better. Losses, you try to get lesser and lesser losses every time. For accuracy, you are trying to get better and better at every point of time. Yeah, Chandra, please tell.
So test loss generally should be above train loss, right? Because in training we are changing weights to minimize the loss, but in test we are directly
No, no, these
using
are independent. They are independent. No, no, no. This is like a kind of a myth. No, it is not so. It can make sure, it might be possible your training scores are less, but your test scores are very fantastic. That means your model is very robust. It does well on the unseen data.
But this is counterintuitive, right, sir? Because when we generalize, basically the loss and errors should be a little more, right?
No, no, I don't think so. This should be our concern because, see, we don't know what this data set is, right? So it might be possible that, yeah, during the training time, I was having a hard time explaining the model, what it does, and those kind of things. But when it came to the test part, it had learned the things so well that it was able to achieve better results. So this is possible. This is not a point of concern, I think so.
Okay.
So now we can see the accuracy. Yeah. Interestingly, our train accuracy is less as compared to the test accuracy, which is mostly lying in the range of 0.9 from the second epoch itself. That is the third epoch. Third epoch, when we say in terms of one. So our training accuracy is still around 0.7 and it goes up to 0.85, but our test accuracy has achieved 0.9. Okay. And you see, the data set sample is very less. Only 225 samples were there in the trained data set and 75 samples in the test data set. So it is not a very huge number. So it clearly means that we lack some data points, maybe. So that you have to remember. Okay. And what finally what you can do is you can also see for which particular how the model is performing for some random samples. Okay. So we'll do that now. Yeah, Chandra, please tell.
Sir, the value of loss, right? So
Mm,
I can understand the accuracy because it will lie between 0 and 1. But
mm.
how to make uh, analyze the loss values, right? So they can go to very small, like less than zero point 0.1, less than 0.05. But we don't know that what loss would be good, right? To what value it should go.
No, that's what we are trying. We are trying to achieve zero loss and best accuracy, right?
Mhm.
I didn't understand your question. What is the
Sir,
question?
what I'm trying to say is that we start at 1.1, right?
Yeah.
And let's say we go to zero point 0.1. Okay. So zero point
Okay.
0.1 means that 10 times we have reduced the loss. Okay. And we might
Mm,
be just very happy that we have come to zero point 0.1, right? But
mm,
if some we don't know how better you can do, right? Because if you, let's say you go to zero point 0.01, then you have again 10 times reduced your loss.
mm.
So we don't know the bigger picture. We just know that okay, it is like reducing and it came to this level.
Yes, that's true. Then
So because this is like a absolute scale, probably I mean in a way that we don't know the range or something.
no,
Uh,
but we know one thing for sure. No, we are trying to go as low as possible. We
yeah,
don't
that
know
is right.
what is the maximum low that is possible. Obviously, before starting the training of the model, you don't know where you want to go, but you know for sure that you have to get better and better every time. That's what you can maximum. That's what you can maximize. You can't do anything else.
Yeah, so for example, yesterday when you showed one of the graphs, right, for AlexNet or GoogleNet, you
Hmm.
showed that it basically adding more and more layers. After some time, the loss basically increased, right?
Yes,
So,
it's saturated,
so
and after that, it started increasing.
yeah. So by this, we just know that we have reduced the loss, but we might still be very far away from that global minima
Yeah,
or
yeah.
like,
Okay, see, yeah, I understood your point. So that's the place where you use that early stopping criteria, right? So if it reaches a plateau, okay, you don't have to wait so that it increases also. Once it reaches a plateau, you can stop that. That is known as the early stopping criteria. So you check for some epochs that if your losses have started to do not go as usual at the rate it was going earlier, then you just stop that particular training.
Mhm.
You don't have to, yeah, it might be far, much far from, I don't know much far about much far, but yes, it might would have gone lower as well because it is completely a steep curve right now. So if you train for more number of layers, it first of all it might reduce, and then it will reach some kind of a plateau. And once hits the plateau, most likely it will go above from that.
Yeah.
So for
Okay.
that only we use this early stopping criteria.
Sir, I sorry, I didn't know that, but yeah, if there is something which we can, yeah.
I think so. It might be present in the next example. Otherwise, if it is not being covered, don't worry. But yeah, for general purpose, I'm letting you know. You can go and explore the documentation for this. What is the early stopping criteria? And it allows you to go till that. See, I'm currently working on my CPU, so
Mm.
it will not be very efficient. My RAM will after some time it will explode. This CPU will get lost and it will say connection timed out. So for that you have to use GPU and you do the training. You do not tell what is the number of epochs. You perform the training till the time you hit the early stopping right. So you can
Okay.
change a little bit of code there.
Mm-hmm.
Then what you are saying, you can achieve that part.
Sure, sir.
Uh,
Thanks.
Is it clear? Yeah.
Yeah.
Okay. Okay. Yeah. This is the same code that we were using earlier. So we are just in the inference mode now, and we are just trying to see. I'll just run this once. Yeah. See. So the true was this should have been a sushi, and it shows me that it is a steak. Uh, True pizza, pizza, steak, steak, sushi, sushi, pizza, 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 sushi, sushi. Yeah. So you see more. So this is a random thing. If you change it once again, it will give me some other. So see, this time something else came, right? So this is just the same thing that we were doing earlier. We were saying earlier what we wanted. We wanted to see how much, what kind of images I have. Now I have the images. I have its true values and I have its predicted values. So based on that, I'm just trying to visualize how good our model is. So it looks through the model that this guy is a pizza. Okay, but though it is a sushi, so it is in red in color. So this is just what we have written, nothing else. So this is a PLT title for that. So with this, I think so we have completed the entire image classification with transfer learning. So at any point of place you have any doubt, you can please let me know. Otherwise, we'll take a 2-3 minutes break and then we'll start with the image segmentation with Unity.
Sir, that last code, I missed that what you explained, but I just want to ask that the images that you have taken, they are from the test data
Hmm.
only, right?
It
These,
can be from any place now, no? I think so. See, range len of dataset. It is from any other, any, but most likely it will be, yeah, it will be from your test dataset. We are testing it on test dataset. Yeah, it will be on test dataset.
but it can
Test,
be from.
see?
Yeah.
Yeah, yeah, yeah. No, 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 no. It is from test dataset.
Okay.
Dataset has been defined as test dataset.
Okay. Sir.
Sir, I wanted to check one thing that we are having almost like at a daily level, uh, both the theory course and on weekends we have the project related sessions. And
Hmm.
all these sessions uh, for working professionals it's not possible to sit through entire sessions. And what
Yeah, true.
happens is uh, so I have been creating a backlog. So every session I start, I attend for some time, then I think that I would be able to cover the latter part of it, but there is some backlog being created for me.
Hmm.
So what would be your advice, both from learning perspective and exam perspective? What should I do? I feel
So,
more time is needed, but I'm not able to find, and backlog is getting created.
uh, so little bit like problems will be there. I can understand that, but I would suggest that from exam perspective, so you have to focus. Like if you are preparing for your quiz one, okay. So if you are preparing for quiz one, then your theory and mathematics should be strong. How, if let's say you have an image of particular dimension and you do this convolution operation, you give a particular kernel. So those kind of maths, those CNN maths and then backpropagation maths, you should know there might be some questions related to that. And if once, and you should know, see, most in the session itself, we have covered most of the code snippets. You now know what each line is doing. So that is enough for you. But once you move to the NPP stage, during that time, you should know how to write that code. So go step by step. That would be better. That would be my best advice.
Sir, what would be the format for NPP? Like in Proctored, we have a Proctor, but here,
Yeah.
what
The
exactly would be
Proctor will
happening?
not be there. Proctor is not there, but you will have a specified time period within which you have to write your entire code, and there will be some problem statement. It might be, most likely might be all on Kaggle. That's how MLP, DLP, those kind of subjects also run. So based on that, you will given a specified time period. I don't know what that will be decided by the professor and instructors. And once that is done, you have to do your and submit your code within the specified time period. That is the general layout how the
Time
NPP.
period means like 1 day or 2 hours. Like,
We can't say. There might be, there have been NPPs of 2 hours, and there have been NPPs of 2 days also. So it depends.
because, for example, if it is, let's say, a one seating kind of environment where you have to, in one seating, you basically finish the problem and the answer, then I think that that requires much more hands-on, right? Where you basically are you can write in one shot all the correct code, right? But if it is, let's say, 1 day, right, I have time, so I can basically write a piece of
See,
code, then get back to my work, and then maybe get back again and
NPP
finish
is
it up.
like in DLP course that was conducted earlier, that was mostly 2 days, right? So I think so. It should be 1 day or 2 days, something like that. It will not be most likely in one sitting. It is not practical because there is lots of coding to do. But I'm not sure. I cannot say per se how what will be the outline. That has still not been told to us, so I can't comment anything on that. But most likely it should be more. You should get a more than one sitting, obviously.
Sir, will it be group or individual?
That is for sure individual.
Okay.
And sir, is this like a open book exam kind of thing?
Yeah, but you will still be checked for plagiarism and all those things.
Okay, okay, sir.
Any other doubts?
But sir, if we follow these sessions, what you are teaching us and what instructors are going to teach us, then we should be able to complete our
Yes, if
NTP, right, sir?
yeah, yeah, very easily, very easily.
Okay, sir.
So now see from just one from yesterday's to till today's session, in approximately 1 hour 45 minutes, we have covered the entire pipeline for image classification. And I'll be sharing this notebook with you guys. So after this, I don't think so. You should have any doubt. I've explained you each and every line of this entire code base. So after that, you know what each of these thing is doing. Based on what your problem statement is, you can change it, tweak it, and use the concepts that are already present. Use the functions that are already present, and based on that, you should be able to do the questions easily. That is what my I think. Okay. If there aren't any doubts, we'll move to the next piece of thing that we have to do this week. That is the image segmentation with the help of UNet. Okay. So let's start with that now. So I'm writing everything in one code snippet only, so that you guys can refer to it. Um, mm, segmentation with unit. Why did it come like this? Hmm. Okay, so first thing is always the imports. 1 minute. Check. So we have to download the Kaggle Hub for this. So basic basic things. So we will code pip install and I can say to dev null. So that will be quite naked. So yeah, this will happen till that time. I'll tell you in a minute why Kaggle Hub and JDown is being used here. Uh, so Kaggle Hub. Code. Yeah. So earlier, what used to happen was that when you had to download the data from dataset from a Kaggle, the Kaggle either you can download directly in a zip file or in a CSV file. You have to go to that link and from there you have to do that. Now there was another method that you can use a Kaggle API, and the Kaggle API had to given a particular API key, and based on that you can use that. Now this Kaggle Hub, what it helps you, you just put the final URL of that particular image. This is the person who has uploaded it, the username, and after that just use the dataset link and it will get downloaded. If you now see here, uh, there it is, where it is to do present here. The root cache Kaggle datasets, root cache Kaggle datasets, where it is. Okay. Oh, it has yet just now extracted thing. Now we need to write something more to class root here. Okay. Okay. Just to let you know what this image segmentation means. I don't know whether you guys, some of you would have seen in the domain if you are from that domain. So what we are trying to achieve here is the leaf segmentation dataset. So leaf segmentation means, let's say you have a particular leaf, and on top of that, it has some kind of a disease. So if you would have seen, so disease can be like yellow spots, there can be brown spots, the insects have eaten it, something like that. So we are trying to segment those portions where this thing has happened. Okay. And so in your train data set, what your train data set will look like, it will have the actual image of the leaf, and on top of it, there on like not top of it, but it will have a corresponding mask. What is that mask? That mask is related to the dot that yellow region, yellow, black, brown, whatever region is there which was affected. So similarly, if in another domain, if you see in MRIs, right? Let's say you take a cancer data set, so you have a full MRI for that person. And let's say you pick a brain cancer data, right? You will have the full MRI, that T2, T2 flare, those kind of scans will be present to you. And based on that, you will have a segmentation image. What is that segmentation image? That segmentation image will tell you with respect to the brain of that particular person, where is that particular tumor present. So it will color that region. So what you have to do, you have to overlay it. You take the train image, you let's take the first image that is from the train, and you on top of it you apply the mask. When you apply the mask, it should be same to same. The real places where that image was, if that, sorry, that leaf or that human being had that tumor, or the leaf had the disease, on top of it when you keep the mask, it should correctly segment out what is the diseased out portion and what is the normal portions. So this is what we are trying to achieve here. Okay. And in the test, what will happen, we will try to define the this We'll try to come up with the prediction for the palm masks. Okay, your test data will have a original leaf image, and you will come up with a mask that should be accurate. This is what you are trying to do. I don't know why I'm not able to see it here. I think so. This is going into cache memory directly. Okay. Yeah. So this is the basic things. We have done it now. You have to import the libraries. Is everyone clear what we are trying to achieve here? Yeah, very
So
good.
can you please repeat what are we trying to achieve?
What to be repeated? What did you not get? Please tell.
So, sir, what is our, I mean, use case here? So what we are trying to actually, for example, what we are trying to access. So we
So
are
it is
trying
a
to see whether it
segmentation
is
task.
disease.
It is a segmentation task. This is a leaf segmentation data set, leaf disease segmentation data set. And in the training data set, you will have a particular image of a leaf. It will be diseased. It might have yellow spots, brown spots, something like that. And there will be a mask corresponding to it. The mask means that where is the particular regions in that particular leaf image which are affected. And in the test data set, you will be given a leaf image, and based on that, you have to come up with the segmentation mask. This is the end goal of this image segmentation
Okay,
task.
understood, sir.
Import libraries. Okay. Yeah, we don't need things. So OS, zip file, NumPy, Pandas, computer vision, PIL from image, TQDM, and Matplotlib. We'll also get the torch libraries, torch vision libraries is also needed. We'll see how to do that. Okay. So now we have to do the dataset exploration. Dataset exploration. Yeah, obviously each image will have a different class. Yeah. So data exploration and reprocessing. Okay. So we'll see some of the images right now. Uh, First, yeah, from PIL, import image. We have the train image. So this says that you first list out all the train images and you list out all the in the sorted order in the train mask. Once you have sorted them again, like sorted. So because sorting is very necessary, because the corresponding images and the masks should be same. It should not be different. Okay. So for that, this is important. So we have now our sorted train mask list and sorted train image list. Okay, we will check what is the data set length. So data set length, images are 588 and masks are also 588. Okay. So we have to now examine what are the data types and what are the dimensions that we have. Okay. Okay. So data type and dimensions both should be same to same. There should not be any difference. So image path, you just bring the image path and mask path. We open the image and we open the mask and we have to check. Yeah, mask is also an image. Yes, yes, yes. Image dimension, what is the data type of that image? What is the mask dimension and what is the data type of that mask? And we'll see what is the in NumPy how it is being transformed. So you can see the image dimension is 326 cross 225. Similarly, your mask is so your data type for image is JPEG and your mask is a PNG. That is also an image. So that is also same. The dimensions are same 326 cross 235. And in NumPy, it is being saved as a U integer 8. Yeah, I think so. It should be on something round integer, something like that. Okay. So U int 8 for both image and mask. So now we will do some, yeah, please tell.
I think so. I
You are
don't know.
not audible, Subrat.
Sir, what is the meaning of this PIL after data type bracket PIL? Sorry, sir, I don't know this meaning.
Yeah, we are so, you would have seen in the earlier image segmentation example also, and in this example also. So PIL, I don't know the full form of that, but the major task that it is performing is that it is taking a particular image and to help us to view it. We need a particular software. We are using a Google Colab
Yes.
and yeah, Pillow. Yeah, thank you. So we are using a Pillow
Okay.
to it is a library itself. It is a
Yes, yes,
itself a
below is.
library. Yeah,
Okay,
so
sir.
it is mostly used in the computer vision tasks to view it, to change it to some particular dimension. So for that we use PL.
Okay.
Okay. So yeah, data. So now we will do some data visualization to see what kind of data we have right now in our hand. Yes. Uh, yes, it should be there. Yeah, just a minute. Give me a minute. Copy this. Yeah. Just explain this once, and then I'll run this. Okay. So image mask pairing we are doing. Okay. So image we take an image from an image path. Mask we take it from the mask path. So figure and axes we define in the subplots. So we are saying that in the first you take the image. The title will be image, and on one side there will be an image, and on the other side there will be a mask, right? And for I in range of three, we are taking random three images. So val images list in locals and val mask list in locals. So that is the we are taking from the train image list only. Okay. You have to take an example of image path, example of mask path, and then you just write, just show me that image. So image is I plus one. So I in range of three means 0, 1, 2, and it will be written as image one, image two, and image three. Okay. Just run this. So why it is not showing me anything? Uh, okay, there is some problem. I told her this data set was not showing here. That time I was not sure. Now it's not working. Mhm. Okay, let's try it. Basic things. What we can open this in a new folder. I think so that will be better. Uh, okay, I'll download this. So I'll give you these two notebooks separately. So I'll just download this. FUINV. Yeah, yes, this is done. So now what I'll say, I'll just delete this entire thing. Very good. Now in runtime, I'll restart, disconnect and delete the runtime. Okay, now this is deleted. Yeah. To run this again. Okay, run this. Still, it is saying it is empty. Hmm. Okay, we will not spend much time on this then. I will just take the sir's notebook and I'll explain it from there itself. It will save us time. You can see this notebook, right? Can anybody please confirm?
Yes.
Yeah. Okay then. So I'll explain you guys from this only. So I'm not running it because most of the cells have been done here. So at least it is working. Yeah. So on this, we were working on this, right? So we are trying to get the image and mask side by side. So now you can see this is an example, image one, and this is our image. Now, if you see very carefully, this is the portion where the black spots are present, and similarly, wherever the black spots are present, it is showing you that in red color. Okay. Now let's see for this image two. This is on the borders, and only border is affected. Little bit of middle portion is also affected. So it shows like that. It is in the red color. Then similarly, it goes for image three. The whatever portions are there, it shows in red color. Okay. So this is how this is what we are trying to achieve. So we are trying to achieve that this, if given a this image, I should be able to recreate this particular segmentation mask. Okay. And UNet is particularly good at this, so we will be using that model. So we are doing our core imports that is necessary. Torch functional optimizers, Torch Vision. From Vision, we get the models. We take our data sets and data set loader, those kind of things. A data loader and transformers. We use the transforms library to the. If you remember, we prepared a pipeline earlier. Also, we'll do the same thing here. We create an image folder, utils.data, data loader, and data set. And from optimizer, we also need a learning rate scheduler. So learning rate will change over the period of time. And augmentations. For augmentation, if you remember, I just told you that what is an augmentation. So for that particular thing, for that also inside this library, we have albumentations as A and albumentations at PyTorch. Import two tensor v2. Okay. So now, first of all, we have to configure the hyperparameters and environment setup. So CFG, we are just doing, so this is a random class. In this, we are defining the torch as CUDA, automatically use the GPU if it is available, and split PCT. Now, splitting the parameters means because if you remember in this, we did not have a train and test data set. So we will keep 20% for validation and we will keep the 80% of the images for our training. So 588 number of things were available to us. So learning rate is 10, I think so 3 e raised to the minus 3. So it is approximately in the range of 10 raised to the minus 3. Okay. Batch size is 4 and epochs is 3. So we define the seed, np.random seed, torch.manual seed. So this has been defined by set, so we don't have to change anything. And finally, we check whether this entire device configuration is saved to my device, and it was saved on CUDA. Okay. Now we do the data partitioning. We have this train set and validation set. If you remember, we have used in CFG, we said that split PCT will be zero point 0.2. So based on that, split PCT, so 0.80% of the images will be given to image list, and from the image part, and from mask also it will go 80%. And remaining whatever is left, that will go into the validation of images and validation of masks. So now approximately 20% of 588 is 170, therefore 80% is 471. Now you have to write a custom dataset implementation because you are doing a segmentation task. So we say the segmentation dataset. We take the image list, we take the mask list, and we have to define the transformers. Right now we'll do that. So we load the image and mask from files. Image path, we perform the image path and take the image path and mask path. Images are in three channels RGB, whereas my mask is only in the grayscale. Okay, that is one channel. So that will be 1 cross 326 cross whatever the height and width. So I think so height was 326 and width was something different. Okay. So convert to NumPy arrays. We are converting it into NumPy arrays, np.array image and np.array mask. We have to binarize the mask to 0 for background and 1 for foreground. So if you remember, you saw one of the examples, right? So entire everything was in black in color. That was the background, and your front was in red color, right? So that is the foreground. Apply the transformations if specified. So we will specify later what are the kind of augmentations we are going to perform on the image and mask. So we have already said that we will make it. I think so. We defined it here, right? Don't know. We defined it somewhere that our image will be an RGB scale image, and this will be a one scale. That is the grayscale image. That is defined as capital L. Yeah, here we defined it that. Yeah. Okay. So these are the yeah. So after that, you have to specify that we will reshape our mask to the channel dimension. So mask dot shape remains same, and mask dot shape height and width remain same, but you make it one cross height cross width, right? So that's how you transform this to a grayscale image. After that, you do the transformation. Your train transformations is resizing because you are going to perform unit. So that will be 512 cross 512. Rotate is with how much rotation you want, 10% probability. Horizontal flip. So I told you earlier also, these things are necessary to make your model robust so that it is resilient to whatever kind of changes you want to make. Either you want to make a flip or you want to make a particular rotation. For those kind of things, it is important to make sure that we change few things in train dataset itself so that you get the best model, robust model. Okay. And then we are normalizing it. If you see this mean and standard deviation, we are just changing it to a standard normal distribution with the maximum possible values of 255. And finally, we change it to the PyTorch tensor. We have to remember that these things are not same applied for the this rotate resize is important because you can't input to a unit model otherwise, but rotation horizontal limit is not required in the test data set while doing the evaluation. Okay, so we just do three things here: a dot resize, a dot normalize, and to tensor v2. Okay, these things are defined. After that, we just take our train image list and train mask list and create a train dataset from the segment with the help of the segmentation dataset class, customized class that we created just now. Okay. After that, similarly, we do for the validation dataset. And now if I want to see a particular image, so what we can do, you see, this is the train image. This is in RGB scale. It is completely white in color. So grayscale image looks like this for the particular image. From validation, we have taken example from validation. This is from the, I think so it is from the train dataset, and this is from the validation dataset. This is the image, and but not you tried. Fine. Okay. And for that, we have a particular segmentation mask. Yeah. Any doubt so far? Anything that you didn't understand? Any particular line of code you didn't understand so far? Please let me know.
The mask one, can you explain?
Which part? Please state.
Masks and mask.
What
Really?
mask and what doubt? What is the doubt in mask?
So, sir, actually, I want to understand that how we are masking. So, what is the corresponding code for masking the image?
We have not written that yet. Means it is
Okay.
available in the notebook, but we have not written that yet. So these masks have already been given to you. You are just taking the correct image. That's all. For now, you are doing this, but later in the final, we'll see. I don't know whether we will to see today or not. But what we are trying to achieve in the end, we will see this code where this image, given a particular image, any new image, it should be able to mask it. Okay. Any other doubts? So, like so far, if you have any doubts, please let me know. No? Okay. Then I'll move ahead. So then we have this train data loader, and the similar thing that we have been doing so far. We change the train data set into a loader, and it becomes train data loader. And finally, we have a validation data. So now your size for the train data loader is 4. This is the batch size. 4 is the batch size. 3 is the number of channels. 512 cross 512. Your images have been now transformed. Okay. So now we finally bring this UNet architecture that we'll be using. So this is a double convolution in channels, input channels and output channels. So you have defined the convolution. This is the first convolution layer. You do con2D, batch normalization and ReLU. If you remember, you have studied this same thing in AlexNet also. So the AlexNet and UNet, they were very close to each other. So UNet was, I think, so came earlier than um, this AlexNet model, but more or less it uses the same thing. First, you have a convolution layer, then you have a batch normalization and ReLU. Okay. So we define the paddle, left tensor and right tensor. If the sizes are not same, then you have to give it a padding, and this padding also goes into the this device. And similarly, you return the right tensor also. Now, what is the model architecture? Input channels. I think so. Input channels have 3, and n is the number of classes that will define. So we have 5 convolution layers. One max pool is there. Is okay. So UNet. Okay. So I'll just let you know what it happens here in UNet. Why it was given the name of UNet. Okay. So the structure, the architecture looks something like this. Okay. Now when you are going down, it is down sampling, and when you go up, it is known as up sampling. Okay. So I'll take a text pen. Yeah. So the image is like this. UNet model looks something like this. While you are going down, you reduce the number of this samples. That is known as a down sampling process. This is the up sampling process. Okay, that's why it is written as down con 2, down con 3. So this is what you are doing here. Okay, so yeah, so this that's why this was given the name of uh, UNet. Okay, because the structure is something like that. And why it is being used? Because see, you are trying to achieve a different type of task here. You are not focusing on just a classification. So what is classification? When you do the classification, it is just one thing. So you go like linearly, you go and you just have to tell whether in um whether for a particular image which class it belongs to, right? But here you are given an input image, but you have to output another image also. So when your input and output both are images, then you have to come up with something solid, so that your mask that you are creating this mask should be appropriate as for what was the input, right? So this is what we are doing. So this input 3 cross 512 cross 512 image will go inside this. It will go and it will continue to downsample. Okay. So if you remember what is the downsampling, so the number of filters will increase. It will try to capture more and more concept. more and more features. And finally, when you try to upsample, you have to again go back to an image. You have to create a image, grayscale image out of this. That's why we are using this type of number. Okay. So after UNet, this YOLO net also was there. Most of the time people use YOLO nowadays, but UNet was the first of this kind, which was able to do this architecture. So decoder. So yeah, just another important point to remember is while you are going down, it is known as the encoder. It is trying to encode what are the present features are present. While it is going up, it is a decoder architecture. So it is encoder decoder architecture. Decoder means you're trying to inference something out of it. You're trying to get something out of it. You are trying to get an image out of it. Okay. So this is the code for same. And you do the forward pass. What is the encoding path? You go convolution 1 max pool, convolution 2 max pool, convolution 3 max pool, convolution 4 max pool, and finally you get the bottom of the bridge, right? That is the conf5. And then you start going up with skip connections. So yeah, uh, just a minute, eraser. Okay, so during the expansion with the skip connections, you try to upsample. For upsampling, you need a padder because padder we have already defined. If there is some changes, like if the dimensions are not correct, so at each level you have to check whether the padding is required or not. But this concatenation with skip connection, you have seen that in I think so in the um, residual skip connection. Yeah, that was the residual block in the RESTnet, right? So you do that. X is there. You go to a particular convolution and you get X prime. But what you do, you just add this up and this becomes X prime plus X. So this was the residual skip connection, right? So this is what is happening. And you continue to do the decoder stage. I think so that is 4 in number. And finally you do a 1x1 convolution to get the segmentation map. Okay, so this is the entire UNet architecture. Finally, you do the training process. This will be mostly same as what we have seen. Yeah. Now the this scoring pattern will get different. Earlier we were using this uh, cross entropy loss. Here we use a dice score. Now dice score is a kind of a coefficient F1 score between the predicted and the ground truth segmentation mask. So this is the dice coefficient. How you calculate it? So dice is 2 into x union y because you see this overlapping concept is important because you want your overlapping to be perfect. Even if you get the segmentation, if you put the, let's say you put an image, your leaf image here, and you put the segmentation mask above it, they should be correctly overlapping. The disease portion should be showing the disease, should be visible in the segmentation mask. For that we use this. Okay, so in you see this is the x union y. So what your x is the predicted set and y is the ground truth divided by the absolute value of x plus the absolute value of y. We can add this because both of their images dimensions are same. Okay, so this is what you are doing is with 50% probability. If it is better, then you take the prediction, you take calculate the intersection and you calculate the union. This is the intersection, this is the union. Finally, you train the model. This is same on what we have seen. So I'm not repeating it. And on validation, you just change this to model.eval with no gradient. We don't change any, we disable the gradient changes so that we get our results properly and we don't change the model at all. Okay. Finally, we train this model. UNet model is getting trained here. Epoch 1, 2, 3. We defined earlier itself. There will be 3 epochs and 4 batches. Okay, we have we get a train loss here, and yeah, I think so. Somebody was asking. I think so, was Chandra or somebody, that your validation loss should be higher than the train loss, right? So this is another example which we can see that the train loss was lower, but your validation loss is quite higher. Okay? So now I think so in the inference sir has taken has taken the same example. So what we did here was once you do everything, you just save this file. Okay. Now once you save the model, so model is saved in the with the extension of .pth. Once you have saved that model, you can use that model again without retraining. You can just get your results. So you see, sir has given this particular image, and based on that, it will give that particular thing. Okay. So with this, it gives you this particular. So it is not very good right now. From the perspective also, you can see that image mask is not that perfect. But with more training, with more number of data points, this will get better across the period. Okay. So this is the entire image segmentation and the image classification with transfer learning. So if you have any doubts, please let me know. Otherwise, you can post it on the discourse. And yeah, that's it. Please tell. Yeah. Anybody? Any doubts? Okay. Thank you, everyone. Let's stop the recording then.